So, welcome. It's Gordon Mac Valley again, and I'm currently using another program to record this whole stuff because it's really annoying. I don't know who developed Clipchamp from Microsoft, but I recorded the fifth part, the smallest multiple thingy, for 2 or 3 times, but it always crashed and it's horrible. I don't know who developed Clipchamp, but this person needs to be arrested for crimes against humanity for wasting my fucking time, okay? This was really horrible. It crashed 2 times, it didn't convert my video, it also has a 30-minute time limit. Although it has this really nice feature of recording screen and webcam together, it went completely to shit. So, enough raging, let's get into the problem smallest multiple, which I've already solved, but I'm doing it again because why not? So to explain this problem, I have already pre-worked it and pre-prepared it back then when I was recording it, but 2520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible by all the numbers from 1 to n? And as you can see, the smallest multiplication of 1 to 5 should return 60. And the way this works is that let's take 5 factorial. That would be the trivial answer if we want to find out which number is divisible by 5 to 1 inclusively. So if you write it as a fraction, you have 5, 3, 2, 1. Let's take the 1 out of here. So if we write it as a fraction and write 2 in there, we cancel out the 2. With 3 as a denominator, we cancel out the 3, and so forth. Now, the basic principle to solving this is rewriting it as prime factors. So, rewriting every non-prime as a factor of prime. So, we have 5 times 2 times 2 times 3. This means to be able to cancel out any number from 1 to 5, we need to have a minimal amount of primes in there to reconstruct every number. So we can just simply divide by 2 and we have 60. Now the reason for that is because of the commutative property and the associative property of multiplication in mathematics, as well as for the natural numbers and as well as for the real number. So this basically means if we write this as a fraction, let's simulate a fraction by a slash. So if we write 2 here, we can cancel this 2 out with this. If we write a 3, we can cancel that out. If we write 4, we can cancel that out because this is 4. This is a very not very good example to show what it's about, but we can exchange it by using 10 factorial, which is this 3,628,800. And we can rewrite 10 factorial as 5 times 2 times 3 times 3 times, so this is 9, this is 2 times 2 times 2 times 7 times 3 times 2 times 5 times 2 times 2 times 3 times 2. And we have the same result. Now let's simulate the fraction again by using the slash. And now we can cancel out the 2. We can cancel out the 3. We can cancel out anything from that. But let's take out the 2, the 3, the 4, the 5 even. Let's take out the 10. 10 is better. Let's take out the 6. And there we have it. So this is 2520. And basically what we are trying to achieve here is list all the numbers from 1 to n, all the prime numbers, and list the minimal amount that have to be existent of a prime number to simulate a number, to achieve a number. So to get the 9 we take 3 squared, so we have to have at least 2 3's in the product, and to simulate the 8 we need to have at least 3 8's and 3 2's in the product. So now we can cancel out 2, 2 is existent, 3 is existent, 4 is right here, the 5 is existent, the 6, because of the associative property we can put the brackets around here, 7 is existent, 8 is existent, 9 is existent, and again 10 because of the associative property. We can associate the 2 and the 5 here and cancel it this way out. So this is the whole principle behind it, and the way we are going to do this is making an array, counting out the primes. What is this? Oh, I need a bracket right here. And let's see. We're going to add the 2 and the 3, so we can calculate the primes until n quicker. So that means we start with I5, so I equals 5 is the next prime number after 3. I is smaller or equal than n, because n could be a prime. So we start with j equal to 2, j is smaller than or equal to then math point square root of n, because if we're checking for a prime, the largest possible number, if we take, like, let's say 14 divided by 2, we would have 7, so we don't need necessarily to go up until 7 to check if a number is prime by using the modulo operator, but we need the square root. For example, 9 is a great example for that. The square root of 9 is 3, so 3 is the limit, 3 times 3 is 9, and then that's the limit to check if a number is a prime or not. J++, and then simply say, flag here, if I modulo j equal to 0 and I not equal to j, so this way we have a deactivated flag that we can use here to break out of the for loop, of the inner for loop, if we have already checked. If we have already checked if the number is a prime or not, if we have already discredited it. So Now that we have this done, we can check if the flag is activated. If the flag is still true, so the number is still a prime, then push the number, the index number, into the primes array. So let's test it. This works, doesn't work. Oh, that's why. I see. Now it should work. Yes, it works. And so now we can do a little prime factorization. So what we are trying to do is to check whether or oops. So what have I done there again? Oh, this is the problem. So we are going to make a new variable result. This is what we're going to throw back in the array. What we are trying to do is count for each prime number how often it has to be multiplied by itself, so to which power it needs to be put by itself to get over the number n, so over 20. This way to do this, we make the factor variable and we set it smaller or equal to 20. We put the primes of I, we increment it. So we are using counter plus plus then, factor times equals to primes I. So if we take the 2 for example, the 2 is the first prime and it will automatically, factor will be in the first step. When counter is equal to 1 it will be 2, when counter is equal to 2 it will be 4, 8, 16 and 32. So when 32 is reached, then counter will be, let me see, it will be 5. So that means, because the last step is done after the checking, when it's also already above, we simply need to result multiply result by the prime to the power of the decremented counter. And if we return the result, we are done. So this is the result we have. So this is what it did basically here, what I showed you here. Skip back if you would like to understand a bit better. This is the whole concept of it. So we are going to check how many primes are at least necessary to fulfill each factor 1 to 20 in the multiplication. And if we run this, it should hopefully work. It does not. Bad. So let me check why. 720 for whatever reason, I don't get it, but let's see. So counter 0. So I guess there is 1, 2 too much. So if we take 2, 2, 3. Oh, that's the reason, right. So now it should work. And we're done. So, thank you guys for watching. I hope if there is any other beginner here, you learned something interesting about mathematics. And feel free to leave a comment if you have anything to add. And up until next time, bye.